So if we get, all right. So guys, we were talking about we started talking about serial link manipulators. Well, how do we number links and joints? The process of numbering links and joints. Remember, we're trying to come up with a unified approach, a standard approach to study serial link manipulators. Manipulators that, as I mentioned before, are identified by these two specific features, that every joint connects two links and every link connects two joints, except obviously the first link, that is the fixed link or ground. These are the specific kind of manipulators or robots that we are interested in when we study the kinematics and dynamics of these robots of robots. And then I started talking about Denavit Hartenberg notation, and I said, well, so far we've been given where the coordinates are, and then considering those coordinates, coordinate frames, we were trying to find a transformation between those two, each two frames, or transformation from one frame to a frame that is multiple frames away, by just using homogeneous transformation and doing some kind of multiplication between transformation matrices. But this gives us a standard approach. So anyone who looks at a robot arm or serial link manipulator, they kind of, at least to some good degree, should come up with the same set of frames and get the same kind of transformation matrix. Now, this is the base. We'll learn how to put the frames. Once we learn how to put the frames on a serial link manipulator, we look into how can we find the transformation matrix between those two frames using this specific notation. Now, I talked about axes. I said, well, there are three rules, I would say, when it comes to DH notation. Before we talk about rules, we said, how do we attach the frames? We attach frame BI to link I at joint I+1. So whatever is the next joint is the joint that we put the link on that for the previous link. For z-axis, I said z-axis should be aligned with joint next joint axis, right? Whatever that joint is. If it's revolute or is prismatic, these are the only two types of joints we're going to refer to in this course. So, and these two joints, revolute is basically the axis of rotation, would be your joint axis. For prismatic joint was basically the direction in which your joint is moving. And once you know the z-axis, x-axis is along the common normal, going from zi-1 to zi, the previous frame z to the current frame z-axis. Now, there are exceptions. If the axes are parallel, obviously there are multiple. You can have infinite number of common normals, but we're going to use the common normal that is collinear with the link. And if two z-axes are perpendicular, there is no common normal, as we said before. So x-axis is perpendicular to the plane formed by two z-axes. And I think you can also add here probably, it's not always, but you can add here typically the direction is zi-1 cross zi. So as long as you know zi-1 and zi, the direction of xi would be the cross product, the plane formed by these two, and the direction would be right-hand rule zi-1 to zi, then your thumb shows the direction of x. It's not always the rule, but typically that's what happens. And once you know xi and zi, you can find the direction of yi. It's a right-hand coordinate frame. So zi cross xi should give you yi. And as I said before, in so many figures you're given, from now on, you probably won't see yi present there. They only give you xi and zi, or x and z axis, because once you know x and z, this rule is, there is no exception to this. Zi cross xi gives you yi, right? As long as you do the cross product between these two vectors, you can think about xi and zi as vectors. it gives you yi, a direction of yi. So that's why you, in a lot of cases, you don't see yi. Now, I said once we set up the frames this way, there are 4 parameters that we can identify, and those are the important parameters we use for DH notation. Now, we introduce AI, so we'll say 2 groups, joint parameters and joint variables. Now, joint parameters include link length and link twist, or AI, sometimes you see it as RI, and alpha I, and DI and theta I as joint distance and joint angle. Now, we talked about this, we can see in the figure, AI is the distance between ZI minus 1 and ZI axis along XI. Right? It's also we refer to it as kinematic length, not that frequently, but sometimes you see that. Alpha I is the rotation required rotation for ZI minus 1 to get to ZI. You can identify these on a figure I put there. ZI minus 1 has to go through to get to ZI, right? And this rotation happens around about XI axis. And remember, I minus 1 just can be replaced by numbers. I can be 1, 2, 3, 4, depending on where you are on your serial link manipulator. Joint variables, DI is the distance between XI minus 1 and XI, right, along ZI minus 1 axis. Again, you can identify that on a figure. And theta I is the required rotation for XI minus 1 to be parallel to XI axis, and this rotation should happen around ZI minus 1. Again, we refer to these definitions over and over, both the definitions of where to put axes and these definitions. You know, at some point you have to you start memorizing these definitions, because these are the only way you can identify the correct value for parameters and where they are. Now, I'm going to give you a good bunch of notes on Denavit Hartenberg approach, because there are a lot of notes there, and you will see these rules can be relaxed sometimes, you can be not followed in very, very rare cases. There are notes about how to deal with what we know so far is still not enough to actually put the frames and make sure the directions are correct. And then I'll go over 3 examples, hopefully, and I refer back to these definitions to identify where to put the frames, and I refer back to the notes I'm going to give you to and mention where we use which of them and how does that come into play when you are trying to decide where to put your frames. All right. And oh, I forgot about that. Just to review, remember I said once we find the 4 parameters, we can actually form a table which is called DH table, or Denavit Hartenberg table. It includes those 4 parameters for each frame. So for frame 1, you identify A, alpha, D, theta. Frame 2 up until the final frame that you have in your manipulator, and identify these 4 parameters. Why do we do that? You will see in the next topic, which probably talk next week, is when we find a transformation matrix between 2 frames. All that matters is these 4 parameters. Once we identify them correctly, we just plug them into the equation, and it's not like before that we have to start looking into the how does the frame rotate to get to the next frame, and that's a very cumbersome process to do if we have serial link robots. For now, just so you know, we can form this table and find these parameters, right? That's essential to actually find these parameters correctly and form the table. And to get there, you have to put the frames correctly, get the orientations right, and identify these 4 parameters to be able to form this table. All right, some notes. So many notes, I would say. Now, let's start with this one. First thing you have to keep in mind is that those 2 angles, alpha and theta, are, as we call it, are directional angles, meaning that the positive direction is determined by right-hand rule. So if we go back here, alpha, remember, alpha is the angle. Let's see if I can erase it. alpha is the angle that zi minus 1 has to rotate about xi to become parallel to zi. Right? We're trying to make zi minus 1 and zi parallel, so we rotate zi minus 1 alpha amount about xi. Now, right-hand rule, to get the positive, so if alpha I has to go in the opposite direction, would be negative. What you see in this figure is the positive direction. How do we identify positive using right-hand rule? Your thumb shows the axis that the rotation is happening about it, and then make a fist. Your four fingers show the positive direction. So if this is xi, this is positive direction. If you end up rotating the other way, that would be negative. Same story about theta I. Theta I is the rotation that xi minus 1 has to go through to become parallel to xi, and that rotation happens about zi minus 1. So we are trying to make zi minus 1 parallel to zi by rotating that about xi minus 1 parallel to xi by rotating that about zi minus 1. Your thumb, look at where the axis of rotation is. Rotation is happening about zi minus 1. Your thumb shows zi minus 1 in the same direction, right? The positive direction of zi minus 1. Four fingers, when you make a fist, shows the positive direction. So in this case, theta I shown in this figure is the positive, right, value. If the rotation was happening in the other way around, it would have been negative. So just keep that in mind, that these angles are directional angles. So it matters what the direction is. It becomes positive or negative, the angles. And for that, you always have to look at the axis you are making the rotation about, right? Theta I are directional angles. Positive direction is determined using right-hand rule. Right. Second thing you have to remember, it goes back to the configuration of joints, and we use that once in a while, not once in a while, I would say probably more frequently, especially when we are setting the direction for the base frame, orientation for the base frame. This one is talking about rest position or home configuration. Now, there is this term, obviously, as I mentioned, home configuration or rest position. And we use that term, it's used to refer to a position, to the position for an arm that we can make as many axes parallel to each other, right? Or if you want to think about those four parameters, it's a kind of position or configuration for an arm. Right? Arm can be in different configurations at any given moment. Is a configuration that if we put the robot in that configuration, all joint variables become zero, or we can make as many joint variables as possible zero. Well, let me just put it in words then. Let's see. Rest, let's write it as rest position for home configuration, right, is the configuration of a robot where all the joint variables are 0. Add this, the best rest position is where it makes as many axes parallel to each other and coplanar as possible. Right. Third thing I want to mention is it's about the x-axis direction. Now, I said here when I was talking about making the x-axis like part 2, I said along the common normal between the zi minus 1 and zi axis, pointing from zi minus 1 to zi, right? That's the general rule. As you see here, xi is pointing from zi minus 1 to zi. Now, here goes the first exception we threw in that sometimes for convenience, we can just forget that condition and we can flip it and make it from zi to zi minus 1. When, we'll see in a few examples, and when does that happen? It comes with a little bit of experience because at the end you want to get matrices that are easier to handle. But just put it here for convenience. We can, let me find what the phrase I use here. We can relax, that's it, relax the strict DH definition for the direction of xi. So it points from zi to zi minus 1. That can be done. And we still are going to get a correct DH parametrization, as they call it, correct values. This happens, this flipping the direction happens. It's just, we do that sometimes when we want to get most parameters 0. Remember, keep in mind that generally speaking, we try to follow the rules and we use the exceptions as exceptions in some situations where exceptions in some situations, but the final goal is to get a table that has as many 0 as possible in as its value. So like this table we form here, DH table, we want to make these parameters 0 whenever we can, as long as we're following the rules. So this zi minus 1, this flipping the direction is something that you will see happens, and you're allowed to do it as long as you can make more parameters 0. More 0, the better, generally speaking. It makes our lives easier. Fourth one, let me see, what should I add here? Let's talk about, all right, just something general. Just so you know, in case it's not obvious so far, the DH coordinate frames are not unique, even if you don't follow any exception, even if you follow all the rules strictly, they are still not unique. Because we only define the line along which zi axis should be. I did not give you any strict way of figuring out what is the direction of zi, right? I only told you, if you go back to the first one, the zi axis is aligned with the joint I plus 1 axis. Now, it could be in this way, it could be in this way, right? That's there, and there is really not that much you can do about it. Someone might come and tell me, well, this is a revolute joint. Why did you take the rotation this way and zi minus 1 upward? I wanted to take the positive rotation this way and zi minus 1 downward. You could do it, right? That there is no rule or specific restriction in DH notation that can prevent you from doing it. So as a result, the DH coordinate frames are not unique, right? So, let me just add it here. Since the direction of zi axis, axes, better to say, z axes, could be for any, z axes are arbitrary. You can just choose any direction as positive. That is going to affect the way the frames are set up. All right, so these four, there are two more that are something that we have to mention them because we're going to use them when we are setting the frames. One important thing is about the base frame, right? You will see that following rules, you can set up coordinates for frames, because for any frame to set up its where it is and its orientation, we need the frame before that, right? We always say, well, this is zi minus 1. So this should be, this rotation theta I should happen about zi minus 1. Now, when we get to the base frame, the one on the ground, there is nothing before that. So then it's become a little tricky. How do we decide about the direction of x-axis there, right? How do we set it up? Because if you go back to definition of x-axis here, or how to set it up, we said it's along the common normal between the zi minus 1 and zi axis. Now, if you are in the base, there is nothing before that. So how do you decide about x direction, right? So you need some kind of guideline where to go when in that situation. Now, in that case, I'll add this note. That the base frame, right, or the global frame, you can think about it because it's fixed, right? It's the ground that we established for the arm we're dealing with. It's convenient to choose the z-axis. First of all, we said the direction of z's are arbitrary, so we can choose the z-axis along the axis of the first frame. Right? So look at the first frame, right? Think about base as frame 0, and then next frame as frame 1. Right? So look at the next frame and see what is the z-axis for that frame. If you cannot, if they are parallel, for instance, this one case, let's choose the direction of the z-axis as the axis for frame 1. All right, and try. Again, try. I know it's kind of vague, and set the directions, right, for the frame you put on the base, where the axes of the frame or global frame or base frame are collinear or parallel with the axis of the first frame. So basically, what I'm trying to say is that look at the first frame, frame one, not first frame, and that one gives you guidelines about how to orient your base frame. Typically, we look at the frame before, right? Because there is nothing before, now we're looking at what is after. All right, let me just write it here, then we'll over examples, I'll get back to it. So let's put it this way. The base frame, or as we refer to it, the global frame, you can think about that. I should have put 4 here. For the base frame or the global frame, I don't know how to put it, it's not confusing. Base frame, they are the same. So base frame, in parentheses, global frame, right? It's convenient to choose the z-axis along the axis of frame B1, the first frame, and set the directions. Let's put it this way. Set the directions in a way that axes of global frame or the base frame, let's say, are collinear or parallel with the axes of frame B1. All right, so again, since we have no frame before to look at, to give us some guidelines how to set that up, we look at the frame after. That's pretty much the gist of it. The rest is details. Now, the final thing I wanted to mention is about the final joint. You have to always make this assumption when you have a robot arm or serial link manipulator, we're to say. You have to make some assumption about the final joint. Is it going to be, is it a revolute joint or it's a prismatic joint? Because if you don't know that, you can't actually set up your coordinate frame for that joint. Remember, there is a link, right? And you always attach the frame for that link to the joint after. And so if you're in your last link, there should be a joint after. Now, if I don't give you the gripper or whatever is the end part, and I just give you the manipulator part, you're going to end up having a link at the end, and you need to know what is the final joint, because the type of joint you get determines where the z-axis is, right? Z-axis is always parallel to the that joint's axis. So when you get to the final frame also, you have to know something about that joint attached to the end of the final frame, connecting that frame to the next possible frame or whatever it is after that. So if that's here is what you can use as rule or guideline. If the, let's say, final joint, I'm going to call it N, following the notation of the book, final joint N is revolute, right, is R, we choose xn to align with xn minus 1 when theta n is equal to 0. Right? That a lot of things I throw there, but I'll try to show you in examples how does this work. If the final joint n is prismatic joint, or P, we choose xn in a way that that theta n is equal to 0. Remember, we're trying to make as many parameters as possible. We want to have as many zeros as possible in our DH table, meaning that there's 0 parameters, 0 value parameters, or the origin of Bn, right? Frame Bn, last frame Bn is chosen at the intersection of x minus 1 and joint axis n, that dn, so it makes dn is equal to 0. So we try to make one parameter 0. If we can't make theta n 0, we make theta n 0. If we can, we make dn 0 by setting up the frames. So these are 6 very important, it's not just typical notes, I would say comments on DH notation and how we can implement that. Now, let's look at a couple of examples and see how can we actually get these to work. I gave you a lot of materials here, a lot of rules and exceptions and things that you have to keep in mind when you're setting the frames. Let's just start with something I would say simple. Example. I do have the picture somewhere. Figures, I think it's DH example 1. Let me just bring it here. Desktop. DH example 1. There you go. Let's figure out what can we do with this. I'll just keep it on the side. For the problem statement, you can write set using DH notation, set the axes, set the frames. Don't even need to be told this, but let me just set the frames for this 2 revolute joints, 2 serial link manipulator, and find D and form, even better, and form DH table. Form the DH table. So we have to find those 4 parameters. All right, so here is the first basic example. We have to implement what we learned. Let's let's go back. We're going to start from where we basically started everything. We have to decide about z-axis, x-axis, and y-axis, right? To have a frame, we have to know these three axes and their orientation, and where do we put the origin for each axis. Now, to decide where to put the origin, we'll look at the first line I put there. We said we attach frame BI to link I at joint I plus 1. Now, before we even get there, let's number these. We talked about numbering, right? I said I start from the ground. This is the fixed one, so this is link 1. Sorry, link 0. Right? We said we number the links from 0. This is link 0. This is link 1. This is link 2. Joints, we said we start from 1. Right? Joint 1, joint 2. Right? If you don't remember this, thankfully I brought these slides with me. There you go. That's what we were talking about here. Right? It's the first thing we talked about, how to number. We start from 0 for links, base or ground, base link, and then for joints, we start from 1. Remember, each joint connects 2 links, each link connects 2 joints, except the base link. So, once we have the numbers there, link 0, link 1, link 2, joint 1, joint 2. We'll go to how do we set the frames, right here. So we attach frame BI to link I at joint I plus 1. Put I equals to 0. We attach frame 0 to link 0 at joint 1. There you go. So here is, it should be, that's where the frame, first frame should be. Maybe a better color. That's where the first frame should be. Right? Attached to joint 1. This is the frame 0. Right? For link 0 attached to joint 1. Using the same definition. Put I equals to 1. So for link 1, we put frame 1 attached to joint 2. There you go. Right? And as I said, you actually have to assume something for the final link. So I'll just, I guess I'll put something there because we need it. But no, let's just not do it for now. Just keep it. So we only need 2 joints.
Excuse me.
Go ahead, Lucas.
The 2R, it's that means two rotations, right?
Yeah, 2 revolute joint basically.
2 revolute joints. Okay.
Basically, this is moving in this way. This one rotate this way, and this one rotates this way. So we have a 2-link R.
Okay, thanks.
So that's where the frames should be. Right? First revolute joint here, second revolute joint here. Let me put R here. And we have the links. Now, that's where we put them, right? Attach them. Now, let's look at the directions, what we are given, how to figure this out. It says the ZI axis is aligned with the joint I plus 1 axis. So, if this is where the frame, it's going to be crowded, so be ready for that, B naught. And this is going to be B1, right? Frame B naught is attached to, is for link frame 0. B0 is attached to link 0 at joint 1. Frame B1 is attached to link 1 at joint 2. Now, ZI, now we have to decide about, that's where it is attached. Now we have to decide about axes. ZI is aligned with the joints axis. Now this is joint 1 is a revolute joint. Right? If it rotates this way, let's assume that this is the direction of rotation. If it rotates this way, we said right hand rule. 4 fingers in the direction is the direction of rotation. Your thumb shows the axis of the joint. So the axis, z-axis for joint 1 is basically an axis coming out of the screen, right? Pointing this direction. Just, I'm going to put it like this. This is z naught coming out of the screen. I showed this as coming out of the screen, coming out in 2 dimension. I use this for going in, or maybe going out and going in. So we have z naught. Now we know direction of z naught. We go to the second joint. All right, so, second frame, B1. For B1, again, what is the rotation? It's a revolute joint. If this rotates this way, 4 fingers, direction of the rotation, my thumb shows what is the direction of z-axis coming out of the screen. Now, as I said, let me just put it here. So this would be z naught. Z naught. Z1, sorry. Things for frame 1. As I said, the direction of z is arbitrary. You could say, oh, I'm going to take the other direction positive. So my z is going to be like going in the screen. That works, as we said. That was the what I mentioned in point 4, right? Are not unique because the direction of z-axis are arbitrary. We know what is the line that the axis is aligned with. We don't know the direction. Direction depends on which direction you take as positive. This is what I did. All right. So far, we are following DH notation procedure, basically. Now, once we get to this point, remember, for the base frame, length 0, we don't have any frame before that. So what we do, we start from frame 1, because a lot of rules we have for DH notation, they require some information about the frame before, right? Or something before and something after, something before, mainly ZI minus 1 is the important thing. So we start always from frame 1, not the base. We start from 1. After we set up where the frames should be and what is the axis of Z axis, we start from frame 1. Now, for frame 1, we want to decide, we want to figure out what is the X axis. Where is the X axis? So we go back to the second note. The X axis, Xi, put I is equal to 1. The Xi, X1 axis in this case is along the common normal between Z0 and Z1, pointing from Z0 to Z1. Now, here goes one thing we have to pay attention. We have 2 Z-axes that are parallel, right? Here. Z0 and Z1 are parallel, right? Both coming out of the screen. They're parallel. So there are infinite number of common normal between them. When you have 2 lines parallel, infinite number of common normals. Common normals means a line that is normal to both. It's perpendicular to both. So what do we do if we have infinite number of lines? You know, how am I going to follow this rule, rule number 2, to set my X1 axis pointing from Z1 to Z0 to Z1? Well, I'm told what to do. When 2 Z-axes are parallel, pick the common normal that is collinear with the length. That means among all the common normals, I have to use the common normal that is collinear with the length 1, and it's pointing from Z0 to Z1. So this is going to be my X axis. X1. Once you know your X1 and Z1, right? You're still on frame 1. You go to third rule, says y-axis is basically the cross product of Z and X. So y1 is z1 cross x1. Right-hand rule is a cross product. 4 fingers along the first element, whatever it is z1, cross the second vector, x1. So 4 fingers along z1, make a fist in a way that your 4 fingers are bent towards the second vector. So along the first vector, make a fist in a way that your 4 fingers go from first vector to second vector. Right? This is direction of the z1. Go from z1 to x1. Right? In this case, it's coming out of the screen. So z1, x1. Your thumb shows the direction of y1. This is your y1. Right? Perpendicular to both x1 and z1. All right. All right. So we figured out frame 1. Any question up to here? It's the first example. So I'm trying to make sure that everyone follows what are we doing. We start numbering links and joints. Then we follow the rule where each frame should be, the origin of each frame. Once we find that, we follow the rule for z-axis. Right? And once we know that, we go to link 1 because joint 1, because joint 1 is a joint that we know something about what is before that. If you start from base link, you don't know anything about the base frame or ground. So you kind of lost there. So start from 1, follow the rules, find out x1. Once you find out x1, you know y1. Now you have frame 1 attached to joint 2. Right? Now let's see what can we do with
Excuse me.
go ahead.
Did you choose x1 because it was a long link 1?
It was a long link 1, following the rule we mentioned 2. So pick the common normal that is collinear with the link. Maybe I should put linear with link I. There you go.
And so in this case, can you point out the references?
Which references? Can you give me a little more?
It's collinear with link 1, and you said something about a common normal, right?
So yeah, so Z0 and Z1 are parallel, right? Coming out of the screen. So when you have two parallel,
Oh, now I see what you're talking about. Okay.
you have two, right? You have infinite number of common normal between them.
Yeah.
Think about in three-dimensional coming out of the screen, going in the screen, like you have infinite number of lines.
Yeah, now I see. Z0 and Z1 are
parallel.
Are parallel. So you draw it from Z0 to Z1.
Exactly. So go from Z0 to Z1, but in this, all the possible lines you can draw, we draw the one that is collinear with link 1.
Mm-hmm. Okay, I understand. Thank you.
All right. So far so good, hopefully. Pay attention to these guys. If you get it now, your life is going to be much easier. It's easier to listen now. I always say that. You're here, I'm here, this is the class time. Use the time and just figure it out right here. All right, so we get frame 1. Now we have to decide about the x0, right, for the base frame. Now let's look at the points we have about base frame. So it says for base frame, global frame is convenient to choose the z-axis along the axis of frame B1. We did that, we kind of followed point 4. I want to take a look at point 2. Rest position, or I don't know what it is. It's home. That's my handwriting that I cannot even read. I feel bad for you guys. Home configuration. So don't even ask me what I wrote. Just remember what I. Oh, because I might not be able to help. Home configuration. Now, what we want to do is we want to get x1 in a direction in which that when we are in the rest position, what is the rest position? As many axes parallel to each other and coplanar as possible. So when we are looking at this, the rest position, one rest position that it's probably very easy to think about is just have all these like this, these two. They're all coplanar and parallel. Now, this needs a little bit of keeping in mind what parameters you're trying to set to 0 when it's in rest position. You want as many 0 as possible in your DH table when you are in rest position. Now, theta I is the angle that xi minus 1 has to go through to become parallel or collinear with xi. Right? It's the last thing I was mentioning here. It's xi, theta. So basically, theta I is the angle between xi minus 1 and xi about zi minus 1. So if you go here, here's what I do. I put my x not here or x0 here. Why do I do that? The angle that x0 has to go through to become parallel to x1, and this rotation is happening about z1, that angle is theta 1. Now, if I'm in rest position like here, let me try it here. So if this is the rest position, if it starts moving at some point, it's like this. Now, if I set my x1 here and y1 there, if my x1 is x0 is in this direction, this becomes theta 1. The angle theta 0. Let's just going back to definition. Where were we? Here. So, theta 1 was right. I'm confusing myself. So going from x0 to x1, the angle you need for that rotation would be theta 1. And you want that angle to be 0 in the rest position. And it's possible by just setting x1 in the horizontal direction. That's how I decided about x1. Now, x0, this is, let me correct that. This is theta 1. Now, I could put x1, x0 here, right? As another option. It could go anywhere, right? I don't really have that much of a rule there. But then when I'm in the rest position, which is everything in like this, aligned this way, theta 1 would have been 0. If x1 is in that position, then I would have had in the rest position like this, I would have had x0 and x1, x2. So in the rest position, where as many, like everything is parallel and collinear, the theta, the angle that x0 has to go through to get to x1 by rotating about z0 would end up in 0. So that's why I choose x not to be there. Once you know x0 or x naught, well, right hand rule, 4 fingers shows the direction of z0, make a fist. From z1 to x1, your thumb shows y-axis. From z0 to x0, y would be in this direction. Y is not really point of interest because once you know x and z, that cross product tells you what is the direction of y. Right. So base frame, depending on what configuration you're dealing with, you can play around with it. Now, is it wrong if you put it in a totally different direction? Technically, no. but then your transformation matrices and the number of parameters that are not zero in rest position in your DH table would increase, which is not optimal for whatever you want to do later on. All right. Now, we said that, we said this. So 2 frames are there. Now, we have link 2, right? So for link 2, remember, we have to attach frame BI. For each link, the frame is attached to the joint after. So for a link 2, we haven't attached any frame yet. And we have to decide what this joint is here to be able to attach the frame. Right? If it's prismatic, it's different versus if it's revolute joint. So let's say I'm going to add this, the final joint is also a revolute joint. Now that determines by what you want to attach to this arm. You know, what kind of gripper, what kind of end effector you want to attach to it. So you have to have that piece of information one way or another, or you have to make that assumption. Say, I take this as a revolute joint. If it's a revolute joint, it becomes the same story as other ones. So this is a revolute joint pointing, it's a revolute joint, assuming that it rotates in this direction. I'll take positive coming out of the screen. I'll take this as Z2, right? Remember, this is, we attach frame for previous link to next joint. Right? Frame BI, we attach frame BI for link I to joint I+1. You can think about this as joint 3. Right? You have to make the assumption, some assumption about the next joint to be able to attach a frame to. So if it's a revolute joint, same story as other ones. I take this as positive coming out of the screen. I have to figure out what is the X axis. I know Z2, I have to find out what is X2. Now X2, again, we go back to what we have before that, between Z2 and Z1, right? Go back to the definitions. Keep going back to definitions. X, we decide about Z, knowing what kind of joint is that. X is determined by what is happening, or how do they stand, how do the 2 Z frames, Z axis between this frame and the previous frame are, how do they are with respect to each other, right? We're looking for Z axis for frame 2, so we have to look at whatever, frame 2, we have to look at whatever is the Z axis or the configuration of Z axis for frame 1. Because we need to go from I-1 to I. Again, we are in the same situation. 2 Z axes are parallel. Since they are parallel, we pick the common normal that is collinear with link I. So, wrong direction. Z1 and Z2 are parallel. So there are infinite number of common normals. Like think about the screen coming out of the screen and going to the screen. Infinite number of lines you can draw between Z1 and Z2. Which one you choose? Choose the one that is collinear with link 2. So this is what you choose. How do you decide about the direction? Well, direction is always from Zi-1 to Zi. So from Z1 to Z2. This would be your X2. Once you know Z2 and X2, cross product of the two gives you Y2. This becomes Y2. Step 1 complete. Now we have all the frames attached. Now let's get to the point that you want to identify the parameters. What parameters? Go back to definitions. We want to identify these 4 because we want to form that table. AI alpha I di theta. Let's start with AI. AI is the distance between zi minus 1 and zi along xi. Starting with put I equals to 1. So the distance between z0 and z1, let me go back to where we were. Sorry, jumping back. So the distance between z0 and z1 along x1, that would be your a1. Definition again. Going the wrong direction. Distance between the previous frame z-axis and the current frame z-axis, or the frame after that z-axis, along that the current frame's x-axis. Again, the distance here between z0 and z1 along x1 would be your a1. So your a1 is, let me form the table directly. And we always start with frame number. We always start with first frame, right? So AI alpha I di theta I. AI alpha I di theta I. Frame 1, we're looking at frame 1. So for frame 1, distance between z0 and z1 along x1, that is L1, right there. All right, let me bring this figure again. Maybe that's too crowded there. Right. I don't know if it helps or not. The distance between z0 and z1 along x1 is L1. So that's L1. It's supposed to be L. That's L1. Alpha 1. Right? Alpha 1, let's see what alpha was. Alpha is the required rotation for z I minus 1 about xi axis to become parallel to zi axis. So here is what you need to just rephrase it. Alpha is the angle that you have to rotate zi minus 1 about xi to make it parallel to zi. So if you plug in I equals to 1, your alpha 1 would be the angle that your z0 has to rotate about x1 to become parallel to z1. Going back to the angle that z1 has to rotate about x1 to become z0. Sorry, the angle that z0 has to rotate about x1 to become parallel to z1. Now in this case, z0 and z1 are parallel, so the alpha value is 0. Right? There is no rotation required by z1 to become parallel, by z0 to become parallel to z1. Both of them are parallel already. D1 is the distance between xi minus 1 and xi along zi minus 1. Plug I equals to 1. So in your case, what we're looking at for frame 1, D1 is the distance between x0 and x1 along z0. Now going back to what we have. The distance between x0 and x1 along z0. You have two x0 and x1. Right? If you think about looking at the screen, this is x0, this is x1. If they were not in the same plane, there was some distance between. There would have been some distance between them along z1. But currently, x0 and x1 are in the same plane. So there is no distance between x0 and x1 along z0. Right? So d1 is also 0. Finally, theta 1 is required rotation for x I minus 1 about zi minus 1 to become parallel to xi axis. Put I equals to 1. So the rotation that x0 has to go through to become parallel to x1. And that rotation should happen about z0. So I'm going the wrong direction. So rotation that x0 has to go through about z0 to become parallel to x1. Whatever that angle is, we can call this theta. Right? Typically, you see that it's called theta. If you think about the line going through that, this is your theta 1. This is your theta 1. So theta I is theta 1, whatever is the rotation that you get when that revolute joint is in action. Do the same thing for the second frame. Frame number or link number 2. Frame number 2. Right? Maybe you should put, I don't know if it's make it more confusing. No, we'll just keep it that way. Frame number 2. So A2 is the distance between Z1 and Z2 along X2. And that distance is L2. Alpha 2 is the angle that Z1 has to rotate to become parallel to Z2, and that rotation happens about X2. I'm not making this up. I'm using the definition. Alpha 2 is required rotation for Z1 about X2 to become parallel to Z2. So you want to make Z1 parallel to Z2 by rotating that about X2. Z1 and Z2 are parallel, so your alpha is 0. Already, you don't need any rotation to make them parallel. Z1 and Z2 are parallel. D2, the distance, again, look at x1 and x2. The distance x1 has to move about 0, 1 to be, let me go back to definition so I don't change. Distance that x1 and x2 have, in this case because I is equal to 2. So between x1 and x2 along z1. Now in your case, along z1, x1 and x2 are in the same plane. So along z1, there is no distance. d2 is also 0. Theta 2, the rotation that x1 has to go through about z1 to become parallel to x2. This is your theta 2. This and this. Your x1 is trying to become parallel to x2 by rotating about z1. So this is your theta 2. This is the motion of the joint. Just call it theta 2. That's it. That's how you form your DH table with these parameters. Right? Well, I only went over one example. I have 2 more examples. I guess I'll go over them next class. So things are going to be pushed back. I went over this a little slow, so hopefully everyone followed what happened. But the bottom line, be mindful about definitions. I put definitions as I minus 1. Just plug in I and I minus 1, whatever the frame is that you're looking at, to make sure that you get the right DH parameters. Now, in so many cases, I'll give you the frames. Right? But you have to be very, very frames. You have to read all the definitions, figure out how can you set up the frames. With parameters, you really have to be very careful. Once you put the frames, just all go over the definitions. So those 4 definitions, in terms of parameters, we don't really have any exception or note. All notes, those notes are related to how to set up the frames. How to find out the parameters, it's pretty straightforward, right? Just those 4 definitions. Once you have the frames set up, you can find the parameters this way. I'll go over another example in the next class. I will see if we get to talk about transformation between 2 JSON frames. All right, I think that's pretty much it.